My name is Kelly. Welcome to this tutorial of the Perturbo Workshop. Today, I'm going to demonstrate how to use Perturbo to compute ultrafast electron dynamics in the Boltzmann transfer equation framework with the example of graphene. I will first walk you through the basic procedure and then introduce some input parameters and outputs. And finally, I'll introduce some new features that's going to be released in Perturbo version 2, such as including the external electric field and excluding some phonon modes, as Ivan talked about. So for the necessary files of this tutorial is all stored on the GitHub repo with the following link below. Let me show you the website where the repo is. You can download all the necessary files. For more details about the physics, please go back to lecture 4 just by Ivan. And for further practice, we'll have another hands-on session where you can follow us step by step Friday afternoon. So now let's get started. A general class of scenarios that can be modeled by perturbable ultrafast dynamics is carrier cooling, just like Ivan introduced. For the problem set up today, we will model exactly this cooling of photo-excited electrons in graphene at room temperature. So the lattice temperature is fixed at 300 Kelvin, and our initial carrier temperature will be at 1,700 Kelvin. You can set it to be anything, but this is going to be our example. For a typical prompt probe experiment, shortly after this excitation of the optical laser, electrons can be described by a hot thermodirect distribution with a temperature of a few thousand degrees. That's why we're setting it to be 1,700 today, and it's a thermodirect distribution. From time equals to 0, we will simulate the dynamics of the carriers cooled in a phonon bath. The phonon populations are fixed and time independent in this case. And for now, we will not include any external electric field. With Perturbo, we'll simulate the full dynamics. And after that, we'll use our Python analysis tool, Perturbo-Pi, where we can plot the electron population as a function of energy in graphene, just like this plot that's on the slide. By the end of today, you will learn how to do this dynamics and also produce a similar plot. So here is the workflow for dynamics. It starts from collecting outputs from DFT and DFPT from Quantum Espresso, generating the prefix _epr.h5 file, which stores all the information of the electron phonon matrix elements in a one-year basis. And after that, we'll go into perturbo.x, where just like the previous tutorial on band structure and transfer calculations, here we also need to first set up to compute the electron momentum grid for the Brillouin zone integration. And after that, we will run dynamics run, which computes the time-dependent carrier population FMK stored in the cdyna.h5 file. And finally, we'll run dynamics PP, which stands for post-processing within Perturbo. And then for data analysis, you can either use any tools of your favorite HDF5 file processing method, or you can use our provided package Perturbo-Pi. Our tool Perturbo-Pi can process either the cdyna file, which stores all the carrier population information, or the popu file, which is the integrated carrier concentration as a function of energy for different time snapshots. All these reference results of today's tutorial can be found on the repo page, and the results are under each folder called references within the subfolders. And for the graphene _EPR file, because it's very large, it's not available on the repo, but you can find it in the example of Perturbo-code. It's under the example called graphene. You can download it through this link as well. Before running the setup, it's actually crucial to compute with calc mode bands and calc mode pH disk to at least see the band structures and phonon dispersions of the material. This is important because we might have different inputs from DFT and DFPT, and then we are also interpolating now in a new one-year basis of your choice. Just like doing Perturbo transfer calculations, we need to make sure that we know the band structure so that we can select the appropriate energy and band windows. So for graphene, for the specific inputs that I'm using, our Fermi level is at negative 4.53 electron volts. And there are two linear functions in our EPR example file. In this calculation, we're only interested in the electrons in the conduction band. So our band min and band max will both be 2, which is the index of the conduction band. And then for the energy window, as long as we safely choose the minimum to be including the Fermi level, and then some maximum of our choice to include all the carrier populations, as long as it converges, then it will be okay. We should choose this energy window as small as possible to save computational time because we want fewer grid points. But then it should be as large as possible to include most of the electron populations so that the results will converge. For graphene, on the plot on the right, here are the phonon dispersion curves. We need to note that the higher frequency phonons are around 200 MeV, and this, looking at the dispersion curves will help us to determine the scale of some parameters, which we will show very soon. So now I'll switch my slide to the right half of the screen so that we can look into how to run this code on the left. So as the previous tutorials, I'm going to export my current directory and run Docker here. I'm currently using GCC OpenMP, and you should run with different commands depending on your system. So here is my Dynamics folder. And here are the graphene EPR file. And then I have a utility script plugin that I'll use later. So before I run anything, let me export the OpenMP thread. Okay. So now we're ready to do setup. So for setup, just as the previous transfer calculation, we have the same input. So first is the prefix, the temperature file. So I'm going to just call it graphene.temper. You can name it anything you want. The first line is number of settings. The second line is the phonon bath temperature in Kelvin, and the chemical potential. If you don't know and you want to determine it, you can input any number. We'll just do 0 for now. And then the carrier concentration, if you want to have a given carrier concentration. So here I'm using this value, and it is 1/centimeter squared because it's a 2D material. Note that for dynamics, it's different from transport, that only the first line of this temper file will be read, as in this line. You can get more temperature settings, but none of these will be actually read by dynamics. And for dynamics, although you can still find the Fermi, the chemical potential using setup, in the dynamics run, these two parameters, the chemical potential is actually not used. Only the phonon bath temperature is read in dynamics run, so that's important. For every run, we also need our EPR file, so let's first link it. Let's first create example file and move our temper file to setup. Let's go to setup. And then link our EPR file. So now I have two things. The last one will be our input. So for input, we can use the interactive workflow on the Perturbo website under the tab Utilities. If you click on the setup calculation, you can find the required files and a sample input file. You can simply copy this, come back, and edit your input. Let me try to copy this again. So this input file contains several things that we need to modify. First is the prefix. You can name it anything as long as it's consistent. And then the next thing is number of dimensions in electron momentum grid. Both KDM 1 to 3 specifies the momentum K points number in X, Y, and Z direction. So for graphene, the third dimension is 1 because it's a 2D material. And then the name of our temper file, ftemper. And then for band min and max, just as I said, it needs to be 2 in this case. So let's do 2. Emin and Emax should be desired, and I was previously saying that I wanted to set it to negative 4.93. As long as it's lower than the Fermi level, it's okay for this problem. And then for the Emax, I need to set it to negative 3.5 in order for the results to converge. The next line is important if you want to find the Fermi level. So let's set it to true. The last line is by default false. So if you're running electron calculations, you don't have to uncomment it. You can also uncomment it and it's fine. But if you want to find whole dynamics, you need to change this line to true and edit the band minimum and maximum energy windows accordingly to fit your valence band. You can also run the whole dynamics, but electrons and whole dynamics for now should be run separately. Now we have our input file, and let's run our calculation. Now we have generated our setup YAML file, which was already introduced previously, and also our, most importantly, the test.h5 file, which contains all the momentum grid. Now we're ready to run dynamics. So for dynamics, we need the previous temper files as well as the TET file that we have. So let's make a new directory called dynarun. Let's link again the EPR file. Let's copy from per setup our temper file. And note that our Fermi level is already computed right here. And then let's keep copying the TET file that we just generated. And finally, we need our input for dynamics. So this is the most important thing. Let's still come back to interactive workflow. Hopefully this time we can copy paste in one go. Here are the input files that you can copy. You can come back and generate the input file. I will quickly go through these parameters, and as I run the calculation, we can talk more about it. So the prefix should be the same as the setup. The K dimensions has to remain the same as setup. And then temper file is the same. And then for the next several lines, these are the time dynamics inputs. The first line, bolt and step, specifies the number of total time steps you would like to use. So if you want to run 100 steps, you should set it to 100. The output in step is however many time steps you want to output one output information. So for example, I want to have one output every 10 steps. So to save some memory, you can input 10 here. If I want 20 outputs in total, but we already have 100 steps, we have to output every 5 steps. That's how it works. So I'll set it to 10, so I have 10 outputs in total. And then the time step is in femtosecond of your time step size. So you can, usually for electron phonon dynamics, it should be around 1 femtosecond up to 10, depending on the system. And you have to tune this parameter for it to converge. The next line, both init dist, is a string that tells the program what kind of initial conditions you would like to start with. For this problem, we'll first start with Fermi direct distribution. So it should be Fermi. Here are the optional parameters. They are optional, but it doesn't mean that you can just leave them like this is. So for solvers, the default is RK4. To save time, you can also use Euler, which is the other option. And then for the next two lines, these are very crucial. You have to modify them. The first one, both init E0 for the Fermi direct distribution will be the chemical potential in the Fermi direct function. You can use any number, but for our problem, our current problem, we would like to use this value right here, right? So we should copy this and modify this value accordingly. The next one, both in its smear for initial distribution to be Fermi, only under this flag, both in its smear is the temperature of your carrier at the initial time in terms of milli-electron volt. Note that this is in electron volts for E naught, but for a smear, it's milli-electron volts. So for example, if I want to simulate it at 300 Kelvin, this value should be around 26. 26 milli-electron volt is 300 Kelvin. But if I want to use a higher temperature, say 1700 Kelvin, this value is around 146. You should calculate the milli-electron volt temperature. The next two lines are what Ivan already talked about, smearing. So the first delta smear is the Gaussian width with which you approximate the energy conservation of emission and absorption process. Usually we set it to 10 by default, but you should change this value according to your grid size. So if you have denser grid, this should be a smaller value. If you have looser grid, this might be larger. And you have to make sure that your results converge. The next line is pH-free cutoff. This is the frequency below which we will set the phonon occupation to 0 completely. This is because we have a BC distribution of phonons, a phonon path. So as energy goes to 0, phonon populations goes to infinity. So this value should be large enough so that we don't have any divergence, but also small enough compared to the overall phonon dispersions. And for graphene, we saw that the highest values are 200 MeV, and then from the graph, it's pretty obvious that 1 MeV wouldn't hurt. So we can just use 1 MeV as a cutoff. The next three lines are the both QDIMs are the phonon grid size. This is not electron, this is phonon. They can be anything as long as they're commensurate and smaller than the K dimensions. By default, it's equal to the K dimensions, the electron momentum grid. But to save time, you can use a smaller phonon grid to start with. So I'm going to demonstrate using a smaller phonon grid. The next line, whole equals to false, should be consistent throughout the problem, whether you're doing carrier or electrons or holes. Band min, band max should be the same as your initial setting. And then both E min and E max should also be the same as the setup. If you don't remember the values, you should go back to the setup file. The next line, load scatter EPH. This is a flag that controls whether you would like to load the pre-calculated electron phonon scattering matrix. You can actually recycle this from the previous transfer calculations if you have the exact previous setting for grid size, energy windows, and smearing. For dynamics calculation, this EPH scattering matrix is automatically calculated if this flag is false or by default false. And then for future runs, if you want to restart a calculation, you can turn it to true. Even if you want to restart from time equals to 0, you can still turn it to true to save some time. And this scattering matrix is stored in the temp directory, which we'll specify here. I'll call it temp. Anything below is only pertaining to the external field, so we'll not worry about it for now. So now we have our input files, and we can run our calculation. So now here it's running through the EPH scattering matrix, and then after this, it will compute the dynamics. So if you want to make this code faster, which is obviously very slow, you can use MPI and OpenMP parallelizations, as Ivan has mentioned. And you also have to modify your comments. For example, you can use MPI run, srun, or any running comments that you have, with the correct number of MPI tasks that you would like to specify. So while it's running, let's introduce all the initial conditions that we can have in Dynamics Run. So currently we're using the Fermi-Dirac initial condition for the carriers. For this setup, the E0 is the chemical potential, and both in its near is the carrier temperature at T equals to 0. But we don't have to have Fermi-Dirac distribution. You can also do Gaussian initial condition. If you enter string Gaussian for any disk, it will initialize a Gaussian pulse with the center of the energy at E0 in electron volts, and then a smearing value, which is the width of the Gaussian, of a certain value of input of milli-electron volts. As I even just mentioned in the Q&A section, that you can also input your own initial condition as long as you modify or prepare a cDyna HDF5 file and run with restart option, which we'll introduce right after we finish the run. We also have Lorentzian initial condition, and for all these inputs and outputs, we can find more about them through the Perturbo website. So if you look at the input files, these are all linked, and you can click onto them to find out more information about them. So the one feature I would like to introduce next is restart, because this will allow you to give your user-defined initial conditions without going to developer mode and modifying the source code. And that will restart from the previous calculations that's already stored in the cDyna file that we generate. Our calculation is actually done, so let's look at all the outputs. So we have the YAML file where we store all the inputs of our calculations and some EPR file data as well. And then we, most importantly, have temp file with the electron phonon matrix elements. And then we also have the cDyna file. Let's look at the cDyna file together. So the structure contains three things. The number of runs, which is 1, because there's only one group. Band structure in rubric units in terms of number of key points and band of our selected window. And finally, the dynamics run group. So in this dynamics run, we have the number of steps. We have the time step of our outputs. So remember that we set our time step to be 1 femtosecond, but that's internally the time stepping time step. But we said that we want to output every 10 steps. So that's why our time step here will be 10 femtoseconds. And we have from time equal to 0, which is the Fermi-Dirac distribution, and then up to snapshot t equals to 10, which is at 100 femtoseconds, which is the end of the run. So there are 11 outputs when we say there are 10 steps. So here is a basic way to do dynamics run, and let me demonstrate how we can do restart from the same output. To do restart, we simply need to have the cDyna file in the same folder, and that's it. So let's first copy pert in to pert restart in. You can also just modify pert in and rerun with the same input file. I just want to do it for clarity's sake to create something new. Here, the only thing that you really need to modify is the restart option here. And what you can also modify is the time stepping. So for example, we already ran previously 100 femtoseconds, but I want to run to 1 picosecond. So I have 900 femtoseconds to go. I can modify my time step to be anything I want. And then I can also modify however many output steps I want. So if I want to output every 20 femtoseconds, I can input 4 to be output in step. And then to run to another 900 femtoseconds, I'll just set it to be 180. Another thing that we can also set is solver. You can also change your solver between runs. But what you should not change is the K grid size and the K grid size and the energy windows. So those should not be changed because that's generated through the setup. If you want to recycle your EPH scattering matrix elements, don't change the smearing, cutoff, or Q dimensions because these are determining parameters for your scattering matrices. And finally, I want to save time by not computing the scattering matrix elements, so I'll set this to be true. That's all we need to modify for now, and then we can do the restart calculation. So if you see, the scattering setup is directly skipped. And for restart, what it does is not generating a new cDynamic file, but instead add another group called dynamics run following the previous one within the current cDynamic file. And instead of starting from snapshot T0, this time we'll actually start from snapshot T1, which is, in our case, we said output every 20 femtosecond, which is 20 femtosecond after the previous step. So remember how many steps we should have? For the first run, we had 10 steps, output steps. And then for this run, we said we want to run 180 steps, but output every 4 steps, that's 45. So if we check the output, we should have 55 steps, right? So let's find out. So let's see our graphene cDynamic file. So now we have 2 runs. The first run is not modified, and the second run should have 45 steps, just we predicted. And each snapshot contains a data set of the dimension, number of K points, and number of bands that's involved in the calculation. Furthermore, we also have cDynamics run YAML file updated here. If you like to save 2 YAML files together, you should probably modify the file names before each run. So if you see this, it's only the second run. Okay, so what we have, the essential output here is the cDynamic file. And that's what we are going to use to demonstrate post-processing with dynamics. Let's make a new directory. And we still need all the previous files. So let's link. Let's link the EPR file. Let's copy from per setup. I think temper. Let's copy the TED file. None of these are changed, so we can just copy them. And then finally, we need the cDynamic run. So for the post-processing input, I'm gonna call it pp.in for distinguishing these inputs. It looks very much like the input file for setup. So you can actually be lenient to yourself and copy the setup input to start. In this case, our calc mode, you should specify to be post-processing, same prefix, same dimensions, same temper file. All these are the same. We are not finding E Fermi anymore in this case. And the only difference we note that is the both DE. Both DE, as the name suggests, is DE. It is the energy step with which you're integrating over the entire Brillouin zone from FNK to get the carrier population as a function of energy at different times. So typically the default value is set to 1 millielectron volts. You can expand it to 10 or 2 or anything as long as it agrees with your precision or your desired values. So now we have the pp.in file, and let's check if we have everything. So we can now run the post-processing. It should be very fast. So post-processing generates some files. The first one is the YAML file. Contains some input parameters of our choice, and also post-processing of all the times vector, the concentration, which is the sum of the electron population, and some timing for perturbo runs. And then the most important one is graphene_popu. So graphene_popu contains several datasets. One is the energy grid electron volts, which is a list of energy values spaced by dE, which was 2 MeV, as we demonstrated. Time steps was 55 plus 1, which the one being T at 0. And then finally, the group of energy distribution. For energy distribution, it's the number of 55 plus 1 time snapshots. And for each data set, it's the carrier population integrated over energy. So it's F of E at different time snapshots. Cool. So with our graphene_popu, we can now go to plot our carrier population with some result analysis tool. So we are currently introducing Perturbo-pi, which is very handy to plot these results. You can analyze dynamics run or dynamics PP outputs. For dynamics run, these are the required files. You need the cDyna, the type H5 files, as well as the YAML file. For dynamics post-processing, you only need the popu.h5 file and the pp YAML to analyze these data. But for time's sake, today, I'm only going to talk about how to analyze the post-processing file. To do analyze dynamics run outputs, you simply need to include the path and load the Perturbo package. You can read more about this in our Perturbo-pi official documentation website. So I have actually written a script called plotDyna, and let's see how it does this. So first, import the Perturbo-pi package, post-processing, and then we set the path of our files needed in the same directory. And then we import our post-processing data from the YAML file using the functionalities from Perturbo-pi, generating this object called, you can name it, for example, dynamic PP, and you can extract all the data from this object very easily. For example, time vector, the time unit, the energy grid, and the population I just saw. And then you can just plot the population as a function of energy at different time steps. So let's run this Python script. I set my own input so that I can choose the number of snapshots I want to plot. So 6 including t equals to 0. It's done. And let's go to this directory. So this is the output that we got. It's pretty much what we showed at the first slide. As long as you plot the electron population as a function of energy for all the time, you'll get the same plot as I showed previously. So this plot is kind of wiggly. It's because we have been using a very small grid. If you increase the grid size to more than 1,000, this will be smooth. If you want to make it smoother, you can also use a larger energy integration step in the dynamics PP calculation. So in order to converge this result, you should increase your grid size and 2 other parameters that I just introduced. So this is the basic functionality of Perturbo dynamics calculation. And now I would like to use the rest of the time to introduce how to run with external electric field. To save time, I have prepared all the necessary input files in the Pert-E field file. So let's go to Pert-E field. So the first thing first, you should still run the setup, which I already ran. It's the same thing as a regular setup. And then for what's different is that for this dynamics, you have to start with a Fermi direct distribution. To do that, you first run a sample run with 0 steps, just to initialize t equals to 0 with the Fermi direct distribution. And then you should run it at 0 field. Let me show you the example. Input file. So everything is the same, but you want 0 time step here. And then initial distribution to be Fermi. You want the energy to be centered at the chemical potential, and then smearing to be your temperature. And here are the E field values in X, Y, Z, and directions in units of volt per centimeter. And finally, I suggest you set both norm dis to be true. This is a flag that if set to true, you'll normalize your carrier distribution every time step. This is very crucial to have convergent results for external electric field. But if you don't have an electric field, you don't have to turn this to true. I already ran the initial setup, and then I also have my temper file. Also, if you want to restart with the temper file, as I haven't noted, you should start with the same number of MPI tasks. I also have, as you can see, the cdyna.h5 file for the initial run. And then after you have the initial run, the cdyna file, you should run with a non-zero field. Simply to restart, input your desired number of time steps, and then at the end, set a non-zero electric field. Let's first run. While we're running it, let me introduce these parameters. So both acceleration threshold here is the threshold below which acceleration of electrons, you will stop the simulation. So if the acceleration is really small, it means that the velocity is more or less converged to the same value and the system is already in equilibrium. So you can stop your simulation before you reach the bolt end step that you set. That will save you some simulation time. And then the next thing is bolt end step min. This is only used when this acceleration threshold is not zero, or this one parameter is meaningful. So this minimum step is the number of steps you have to run before you stop your simulation. So for example, if your results converge after the first 2 steps, but you still want longer steps, longer simulation, you should set this to be larger than 2. And while we're running, let me introduce the other, to stress the importance of converging parameters. So these are all the values of parameters that you really need to converge. The energy windows, the electron momentum grid, smearing for the Gaussian, cutoff for the phonon, and finally the time stepping, solvers and time steps. The next feature that I would like to briefly mention with the example and reference files in a subfolder on the repo already, which you can run by yourself, is to exclude selective phonon modes. You simply do the same dynamics calculation, but add one more line, which is pH mode exclude ranges in Pert-In. You can input up to 30 different ranges of phonon dispersion. So for example, if I want to exclude mode number 567, you should enter 5, 7 here. So that's a range that you enter. And then you can add another range with 2 below and 3 and 4, etc. So this is equivalent to setting the electron phonon matrix element to 0 for the selected number of mode indices. So as an example, if you start graphene with a Gaussian pulse at a certain energy, and then evolve the system, let it cool. With all the phonon modes, the net dynamics looks like the above, but if you exclude mode 5 and 6, the dynamics actually quenched. So this helps us to understand which modes contribute mostly to the dynamics. So I hope this feature is useful. And let's see. Okay, so it still haven't finished yet, but we are running out of time. So I'm just going to show you what you can get from plotting the external electric field. So note that for electric field calculation, for the post-processing, you also have the E field parameters, and you have to set them to be non-zero, which will agree with your previous calculations, dynamic equations too. So after that, you will also be able to plot something like this. We see that this run goes to 10 picoseconds. This is because to converge to a certain population, you need a longer time because now there's way more energy in the system. And with that, I would like to summarize the dynamic simulation. First, we need to run the setup file. Note that there are momentum grid sizes, energy band windows, and then some other parameters converge. Next, we'll go to dynamics run. I introduce different initial condition settings, the restart function, and then the new features such as external electric field and phonon mode exclusions. And then we can go to dynamics PP for post-processing, and finally use Perturbo-Pi for data analysis. So with that, I can open to questions.